Okay, so good morning everybody. It's me again. Okay, I'm going to talk about our CProBio project number 7, which is closely related to WP7 from Sunday. And the subject of this talk is also related to yesterday's talk. So I'm presenting you again this slide, which is the evolved processing diagram that we are proposing for sugarcane processing industry, but actually it applies to other biomass sources. Okay, so remember we are proposing a pre-treatment followed by hydrolyzation process in order to free up sugars. So it involves bioreactors here, and also a reactor for enzyme production, which can be on site or somewhere else. And we are also proposing to recycle nutrients from vinasse by processing this product through a photobioreactor. Okay, so I'm going to talk about efficient large-scale bioreactors, which are applicable here, and also in enzyme hydrolyzation and production. So now I want to focus on the development of high-efficiency industrial bioreactors, and in particular, I want to show and explain some upscaling analysis. I cannot avoid to show you some equations, but don't bother with the language. It's very simple. We have three conservation equations: mass, momentum, and energy. Again, don't bother by the language if you're not used to, because what is stated here is very simple. Mass is to be conserved. This is an equilibrium of forces. This is acceleration. These are gravity forces, pressure forces, and viscous forces. So it all has to balance. And also, energy equation says that the internal rate of energy variation is equal to the energy transported by the flow, and also energy that is coming by conduction inside the flow. Okay, so these equations are very simple, and but they are sufficient to show you what I want to show. They presume that you have an inviscid flow, incompressible, and this is happening inside the bioreactor. Okay, so the idea to see how dimension affects the problem is to transform these dimensional equations into non-dimensional ones by substituting these variables, velocity, temperature, pressure, by the corresponding non-dimensional ones. So if you have a generic variable A, it has a dimension. It can be in meters or meters per second. So the idea is to replace A by its non-dimensional version, which is calculated by dividing it by a reference dimension, capital A, for instance. Okay, so if we do that, for instance, if we elect capital U as a reference velocity, and we create this one, which is the corresponding non-dimensional version. If we do that, I'm coming back one slide, if we replace that in all these equations, we're going to get these new equations here. Okay, the indexes here refer to the common Einstein's notation. But what's interesting to show is that mass conservation equation is the same. Momentum equation, let me highlight here. Momentum equation, you're going to get these new numbers, new variables, or new non-dimensional numbers. Froude number, you get Reynolds number here in front of the viscous term. And in the energy equation, you get Struhl number, Reynolds, and Prandtl number. So you have these equations that states mass conservation, momentum conservation, and energy conservation. But and in non-dimensional variables. So you don't have a problem with the scale. But you have this non-dimensional number, which are defined here, okay? And they actually determine the behavior at the scale of your problem. So you have, for instance, true number, which is a quotient between transient effects and inertia effects. So it's important if you have transient heat transfer. I'm coming back one slide here. So it affects only the energy conservation equation, okay? You have Reynolds number, which is a quotient between inertia terms and viscosity terms. It affects, I'm coming back one slide, the momentum equation and also the energy equation. And you have Froude number, which is important if you have a free surface in your problem, okay? And because it states a balance between inertia and gravity effects, and the Prandtl number, which is a quotient between momentum diffusion and thermal diffusion, and it's intrinsic to the fluid, okay? It depends only on thermophysical properties of the fluid. So these numbers determine the behavior at the scale that you want to study your problem, and the scale parameter here is D, which can be the diameter of your reactor or whatever, okay? So an important consequence of this is that similar geometries may respond completely different to the same boundary conditions depending on these non-dimensional numbers. So you may have exactly the same flow rates and so on, and your system may be completely different. I'm going to give you a very simple example. An isothermal flow past a circular cylinder. So I'm coming back some slides here, okay? So it's isothermal, so you don't have the energy equation, you don't need to enforce it, so you have only mass and momentum. And what we are going to vary is the Reynolds number, okay? So we're going to vary the diameter of the cylinder. So by doing that, I'm varying actually the Reynolds number. So it's only the viscosity term in the momentum equation that's being varied, okay? At very low Reynolds number, you have the flow from left to right, and you have a nice wake behind the cylinder. What's being plotted here is the angular velocity of the flow. So blue, in dark blue, is the flow is almost, it has no rotation. And what is white and red, you have some angular velocity of the flow. So if this is a photobioreactor, for instance, and remember that when you have vorticity, you have shear stresses are very important. So if this is a photobioreactor, any cell that passes through these red regions may die because they will be torn apart by these regions, okay? So by simply increasing the Reynolds number to 110, so it's the same geometry, same velocity here, everything is the same except that we changed the diameter. So we changed the Reynolds number. Now you can see that inertia terms are balancing viscous dissipation. So the flow wants to oscillate, but you have viscous dissipation. So it's a kind of a dynamic equilibrium like this, and you have this oscillation. This is exactly why a flag oscillates in the wind, okay? And again, if you have cells within this medium, well, they are going to have a hard time only in these regions here, okay, where you have high vorticities. And by increasing a little further the Reynolds number, the behavior is completely different. Now you see that you have these vortices being released, and everyone with high vorticity. So cells are dying here, actually. Okay, So remember, this is exactly the same problem. What's being changed is the scale of the problem by changing the diameter of the problem. So if I have a small photobioreactor represented by the first example, cells will have a good time in this small photobioreactor, and if I increase the scale, I have regions, very dangerous region, where cells may die within them, okay? So this is what happens when you increase the scale of the problem, and this actually happens at every scale. This is a satellite picture from the islands of Cape Verde. Okay, you see these wakes behind the islands. So it really, actually, the Jupiter's spot is also a kind of a vortex like this. Okay, so we did some studies. We elected a test case which we wanted to develop to increase its efficiency. We are trying to develop continuous fermenter. They are actually used in practice. They are very simple to operate. They are very inexpensive to build, but they are still very inefficient at these scales. Those ones have a slightly different configuration than the previous one I showed. The input is over here, then the flow circulates within them, then it goes up, and the output is behind the surface here and goes to the other one. Usually you have 2 or 3 or 4 reactors like this, in which you can control, you can impose different fermentation conditions, different temperatures, in order to increase efficiency. But remember, fermenters, continuous or the batch versions, are still the least efficient processes in the overall process. So increasing their efficiency has a very important impact in the overall efficiency of the conversion problem. And what we are trying to, what we did in this test case, we tried to assess the residence time distribution. The concept of residence time is important because, well, it's defined by what we call an ideal or hypothetical residence time, which is determined by the time necessary for the biochemical reaction to take place. Okay, so it's not, it's imposed by nature, let's say. And what we do, usually, we simply calculate in a hypothetical, I would say, or theoretical residence time by dividing the bioreactor volume by the input flow rates. And one of the problems is that this residence time has nothing to do with the actual, even with the average residence time. I'm going to show you. Because depending on each flow line that a particle follows, you have a specific residence time, okay? So consider this example here. You have a flow line that passes right over the guy here. And if you calculate this specific residence time over this line, you just perform this integration. Okay, you calculate the distance divided by the velocity. The velocity is always tangential to the flow line. Okay, so what you have here is actually a residence time distribution, not a single residence time, and that applies also to a reactor. And so our idea was to use a CFD platform to make this upscaling studies. And in this particular case, we wanted to optimize the residence time. Okay, so just some examples here. This is a 10 cubic meter continuous reactor. Input is here, and the output is over here. Okay, so the flow swirls around this central tube here, and you can see the flow lines, and you can imagine that associated to these flow lines, you have residence time distribution, which I'm going to show you just in a few slides. Okay, just by increasing the volume of this reactor, you see that now you have the same geometry, the same flow rate, or the same theoretical residence time, but you see that the streamlines are completely different. Completely different, just by changing the volume of the reactor. And you can figure out that the corresponding residence time distribution is very different. Okay, so what can happen when we calculate these residence time distribution? You see things like this. First of all, here, let's say it's your theoretical residence time, calculated by dividing the volume by the input flow rate. Okay. Here you have your actual average residence time, which is an average determined by this distribution here, okay? And you can see things like this. You have short circuits. Those are particles that take a streamline that goes straight to the output, so it spends, the particles here spends less time than the necessary time for the biochemical reaction to take place, okay? And you also have this region here in which the corresponding particles stays longer than the necessary time. Okay, so this effect and this effect actually contributes to the deterioration of the performance of the device. Okay, you also have, and you may measure these things. You can calculate how the distribution is spread around the average value, and you can also calculate the difference between the actual average residence time and the theoretical residence time. Because when you design your reactor in the first place, you have this time here, which is determined by the necessary time for the reaction to take place. So this is our designing machine or upscaling machine. It's a CFD platform. I showed you this transparency yesterday. Okay, so we have these geometry parameters, we have a mesh generator, and we have a CFD solver. So the CFD solves mass, momentum, and energy equations. And you have, from this solution, you can calculate your optimization parameters, which can be, as I showed you, the difference between the residence time, the actual residence time, and the average in the theoretical residence time. But you can also calculate, if you're designing a photobioreactor, you can calculate the shear stress and so on. So then, by analyzing these parameters, you can propose corrections to the geometry parameters, and you change your reactor, and the process go on until you have an optimum design. Okay? So I'm going to show you some results due to Evelise. Evelise was at Cambridge last year. So this is just an example, just to show you the influence of the input angle. Okay? So you have the height here is 120 centimeters. It's fixed, just to show you the influence of the input angle. You have at 90 degrees, okay, 90 degrees is the input angle here. You have this purple distribution. You see a huge short circuit, and so that's it. This is the worst distribution. An important thing is that the actual residence time is completely different compared with the hypothetical one. And by changing the angle, you see that these distributions, they collapse into an optimum one here. So the CFD platform is changing automatically the geometry of the reactor in order to enforce a thinner residence time distribution. Okay? These ideas can also be applied to a photobioreactor, in which you have to enhance light propagation. So we started by considering this prospective configuration. It's a tube photobioreactor. It's very good for illumination because you have a huge interfacial area, but you have a poor interfacial area for gas exchanges because, well, the area that you have is the section here and the section here. So it's very poor. And as a consequence, you have a poor temperature control. Actually, we are considering this configuration. It's an airlift bioreactor. It's something like this. You have a bubble column here. Light is entering the volume by the external surface here, okay? And you have a flow like this, induced by the bubbles. So what's interesting is that you have an excellent interfacial area for gas exchanges, for photosynthetic O2 removal, and for CO2 supply, okay? Because it's related to the interfacial areas of the bubbles. You can also control the dark light photoperiod, which is important for cell growth, okay? But in this case, you have a poor interfacial area for external illumination at large scale, because if you increase the scale, your volume increases more rapidly than the external surface, so you have comparatively less illumination area. So what we are considering is a slightly different configuration. We start by this, what we call culture cell. We have illumination pole at the center, around which there's a bubble column. So you still have this vortex here. So you still have the possibility of controlling the photo period, but the upscaling process is done like this. You have several of these culture modules here, arranged in rings like this, okay? So we did some light propagation studies. This is the Beer-Lambert law for a cylindrical geometry, okay? R is the distance from a specific point to the light source, okay? And well, the total light intensity at a given position is given by the sum of all the light sources. I'm coming back on the slide. So if you are at a specific position here, you have to add all the light sources which are at different positions, okay? So we can plot the light intensities. What we did here, we just calculated light intensity for a single illumination pole, which is this red curve here, okay? And for the proposed geometry, we calculate the light intensity along this line here, it's R0, and along this line here, it's R30, denoted by these lines here. So the red one is for a single illumination pole, the blue line is along this horizontal axis here, and the red line is the illumination along this line here, okay? And you see that if we consider the single illumination pole case, and if you consider that the above 90 or 80% of the light intensity, you have photo inhibition here. So the cells want to protect themselves, so they don't grow. And above 40%, you have not enough light for the cells to grow. So the useful region here for the single illumination region is indicated by this red rectangle here. Okay, so it's the region between 80% and 40%. If we do the same for the horizontal line here, you see that the useful region is much bigger. Okay, from this position to this position. Okay, now here you have photo inhibition, and along the horizontal line, the R0 region, you have a much bigger light intensities, or a much bigger useful region. Okay, so if you consider now that you have algae within the broth, the culture broth, and you can calculate the light intensities by considering the light attenuation due to the water algae mixture and due to the bubbles okay, to the bubbles. So this formula corrects for the presence of algae and bubbles within the culture broth. And what we did to determine how these things work, we used our CFD. I don't know if I have to click here. Yeah, maybe. And what we did, we calculate the void fraction at this position here, and we adjusted an average void fraction curve, which can be done by this formula. So we adjusted these parameters, this one, and this one. And then we, coming back one slide, we introduced them in these formulas here, okay? Here and here. We can calculate the actual light intensities. This is this red curve here, and also the average bubble void fraction, the red curve, and the average light plus algae void fraction here, okay? And we can calculate those same production regions, okay? So you see that very close to the light source you have photoinhibition, so you have a smaller useful region. Far away from the illumination, you don't have enough light, and you have this useful, let's say useful region for cell growth. Okay, so what we did, we put all these calculations into our designing machine, that previous slide that I showed you, where you have the CFD platform and the optimization method, and we designed a photobioreactor based on this procedure. What we're now doing, we are building a photobioreactor, a 10 cubic meter photobioreactor, in order to verify, to validate all these calculations. Okay, it's also going to be instrumented. We're going to have light sensors and so on, and we want to test all this in order to see if we can obtain high algae concentration at large scales. Because, well, if you look at the literature, you see that very high concentrations are something around 5 grams per liter or 10 grams per liter, and but very small reactors. We want to achieve, this is our goal, these concentrations at these scales. Okay, so conclusions and perspectives. An optimal design method was successfully developed. That is an iterative procedure based on parametric modeling of the flow. So we did this optimization for a fermenter and also for a photobioreactor. And transfer of technology already started. And we intend now, as I said, to build a laboratory/pilot scale small plant to test, and we also want to do a larger one, possibly a 100 cubic meter photobioreactor. Multi-phase flow equations are already being introduced at this moment, and we want to actually implement a multi-objective optimization procedure by optimizing at the same time shear stresses, sedimentation, the difference between the actual and the hypothetical residence time, and so on. So we need to implement a Pareto frontier search method in that design machine. Okay, so that's it. Thank you very much.